So I'm going to go ahead and start the recording, and I'll put that in the kind of general announcements here. Okay, so it looks like we got the recording started. So as I was just saying, the big thing that I think you guys are waiting for is the exams. My goal is to get those graded and back, or at least posted scores on Canvas by this weekend. Early this weekend is my goal on that. And then you'll be getting the exam documents back in lab period next week. So we'll be doing the psychometrics lab, so I'll be handing back your exams at that point. Otherwise, I just wanted to remind everyone that I have posted the second psychometric kind of reading quiz. Remember, reading quizzes are open book, open notes. So that should be something that you should be able to complete after the lecture today. You should have a pretty good basis for most of the topics that are covered in that quiz. So again, that will be due beginning of next week, I think, is what the timeline on that is. So again, I just wanted to let you know that it has been posted. It's available. Also, the homework related to the psychometric processes has also been posted. Again, you want to start those early, work through all of the details on that. But that will begin to be related more to what we'll be covering today in class. The last thing I wanted to point out is I did add a kind of poll survey on Canvas. It's completely optional, but if you wanted to provide any sort of feedback, it's a short little questionnaire about progress this term. So if you have things that you want me to try and incorporate, that's essentially where you'd go ahead and put that in the course survey. So those are the things I wanted to remind everyone of at this point. Otherwise, those were the only things that I had before we wanted to get started, unless there was any questions or anything like that. And so I'm assuming that we aren't going to have many probably questions on that. So without further ado, let's go ahead and get into the detail of our psychometrics and our ideal kind of air conditioning processes. And so basically, if we want to think of it, this is going to be where we take all of that knowledge that we had from our basic definition, and we're going to try and apply that to kind of real applications. And so for psychometrics, the most common kind of approaches that we're going to mainly deal with are going to be open system analysis. And so open system means that we're going to rely more heavily on enthalpy. And so that's why we kind of, in our base discussions, talked more in terms of enthalpy than internal energy. It's because a lot of times when we deal with psychometrics, we will be dealing with open systems. And so that means we just have mass flows, we have heat transfer rates, we have power in terms of our energy balance. Now, the most common applications for these kind of analyses are going to be in the HVAC application. So heating, ventilation, air conditioning is shortened to HVAC. That's where we're going to spend most of our time trying to focus on the psychometric processes. Now, in terms of the HVAC applications, generally we talk about four-ish, and we can combine them together. First, we'll talk about simple heating and cooling. So that'll be related to what we've seen in previous parts of thermo, just heating something up, cooling it down. We'll talk about now humidification and dehumidification. So adding water vapor into the system, pulling it out. From the opposite side, of course, would be the cooling, and then we also have the dehumidification, which is going to be the pulling the water vapor out. And so those are going to be the four basic processes that we're going to end up focusing on in terms of our HVAC kind of analysis with psychometrics. And so these are going to be kind of the fundamental things that we'll talk about in terms of the next few slides. Now, in terms of the main things that we want to talk about, we'll start with the individual processes, and then we'll go ahead and try and put them together, like how we will see them in HVAC applications. Now, there's one more thing that I put on here, and that is going to be adiabatic mixing. And so when we do talk about air conditioning systems, we also do talk about mixing flows together. And so that is just going to be dealing with mixing of mixtures now is kind of the best way to describe that. So those are going to be the topics for the lecture today. And so let's go ahead and get started with our simple heating and simple cooling process. And so in terms of simple heating, simple cooling, what we mean by that is we take our moist air coming in. So we note that this is moist air. We have an initial temperature. We have some humidity ratio. We have some relative humidity. So we'll note that this is basically our moist air coming in. We're going to then add heat and nothing but heat into the system. So we just basically say, well, we have a Q dot into our system, and that of course changes the temperature of the system. So we'd heat it up. So we'd say T2 is going to be greater than T1, and we're going to have moist air leave the system. And so in this type of analysis, we're going to see that we're just adding energy into our system. And in terms of dealing with this, we're going to be using the psychometric chart to kind of understand and visualize what happened in terms of psychometrics. And so this is where the psychometric chart that we talked about on Monday comes into play. And so we want to see what happens in terms of our simple heating when we now put this and plot this on the psychometric chart. And so in terms of the psychometric chart, let's go ahead and say we bring air in. Let's say T1 is going to be, let's use 15 degrees Celsius. So 15 degrees Celsius is right here. And let's do like a 40% relative humidity. So that would give us a point right about here for state point number 1. Actually, I'm going to change colors here. We're going to do this one in red. So that would be right here. Okay, so we will do state 1 is at this point. Now, in terms of what we want to do, we said we want to heat it up. We want T2 to be greater than T1, which tells us that if we want to say heat this up to, let's do 35 degrees Celsius. So 35 degrees Celsius means that we're going to move to the right on the psychometric chart. We have to figure out what direction to the right do we go. Do we move up? Do we move down? What is the actual process here? And so we'll get into kind of the mathematics of how this is going to work. But what we'll eventually see is if we do the conservation of mass for water and air, well, we'd have one inlet for the system, one outlet. And so if we did this for just water vapor going in, going out, we'd have the water vapor in has to equal the water vapor out. The dry air in has to equal the dry air out. And so the humidity ratio, which would be the mass of the vapor divided by the mass of the dry air, we can add dots to those to get those in the flow rates. We see that because the mass of the vapor, the mass of the dry air doesn't change, we said, well, that gives us the definition that the humidity ratio for this process would be constant. And so if we recall from the psychometric chart, the humidity ratio is found by drawing a dashed horizontal line over here to the right-hand side. And so this would be our humidity ratio here at state 1. And so W1, in this case, it's a 4. Let's say that's close to the dash line. So we're going to just guess that's about 4.5 grams of vapor per kilogram of dry air. And so remember, this one had that weird unit system for the humidity ratio. We said, well, all right, so if we know W1 has to equal W2, we can say, well, W2 is now equal to W1. And we said, we know what the temperature is. So to draw a line here, so if we did 35, we go up and we put state 2 on the line of constant humidity ratio. That means we just move straight to the horizontal on the psychometric chart for simple heating. And so this would be state 1. This would now give us state 2. And so we've heated the fluid up. So our temperature, and again, temperature is referring to the dry bulb temperature, has increased in this process. And so again, the key thing that we had to note here was the humidity ratio was constant for the heating process. Now, in terms of the other variable that we want to note, is we want to look at the relative humidity. So that would be our phi. So when we designed our system, or we picked our starting point, we said the relative humidity here at state 1, we said that was along this line, that was about 40%. And so we had about 40% relative humidity in this case. Now, by just using the chart, we can see that increasing the temperature here is going to change the relative humidity even though the humidity ratio stayed constant. And so what we've done is, again, we've moved to a higher temperature, so we've changed P sub G, but we said, well, that is going, and basically P sub V will stay the same because we have the same total pressure, because this is done at atmospheric pressure. And so what we've done is we've now decreased the humidity ratio. And so if we look over here, this would be about 10% relative humidity. Here's a line of 20. We'll say, I'm going to guess, and I'm going to go ahead and say this is about, we'll say 11%. It could be 12%, but somewhere around there, we see that we have the humidity ratio at state 2. And so in this heating process, we've now decreased the relative humidity, but the humidity ratio itself stays constant. And so this is where we'll get into kind of our discussion of systems and why we have to kind of do combined systems of heating and humidification, because we're going to be changing how the relative humidity at these temperatures are when we do simple heating, and human comfort is based on relative humidity. So in that case, we will not be quite as comfortable, even though it's a warmer case, because it's a low relative humidity. And so the key thing to note here is that, again, humidity ratio is constant, relative humidity will change for heating process. And so if we can do this for the simple heating case, well, we could say, well, cooling case, we'd expect this if we don't have any condensate to come out of the system, we'd expect something similar to happen. And so if we go ahead and just repeat this process, so we now have, let's do 40-degree temperature, we'll do a hot, we'll do maybe right about here. So this is 30% relative humidity. Looks like that's not going to stay. So this will be our state 1 for our cooling side of things. And so state 1, that will give us a temperature here of about 40 degrees Celsius. We have our relative humidity 1. This is, what do we say? It was 30, I think it was. Yeah, 30%. And so in terms of the cooling process, if we're not worried about any condensate, we're going to have a temperature 1. We're going to have a humidity ratio 1. We'll have a relative humidity 1. We'll have the same thing on the outlet state. So T1, W2, and Phi2. And we said, well, we do our mass conservation, mass flow in, mass flow out, 1 inlet, 1 outlet for both air and water. So we end up with the humidity ratio 1 has to equal humidity ratio 2 for this process in our cooling. And so as we've demonstrated with the heating case, that means we just move straight on the horizontal. And so we'll end right here. This is going to be straight 2. So we've cooled it down to, in this case, looks about 26 degrees Celsius here, 26 degrees Celsius, so it's T2. And so we see here, we've got T2, we have T1. T2 has now decreased. And so T1 is going to be greater. And what we'll see is we'll see the opposite now for the relative humidity. So the relative humidity at state 2, this is going to equal 60% relative humidity, where we started at 30%. And we did that again just by changing the temperature at a constant humidity ratio. So we'll know W1 equals W2. So simple heating, simple cooling, we'll see humidity ratio equals a constant. Relative humidities are going to be changing. We'll also change our temperature. And so again, the key note here for simple heating, simple cooling, there's no additional mass flows, no condensation, no water vapor being added. It's basically a single inlet, single outlet system that we saw in previous thermal classes. So that is the simple heating, simple cooling case. Now where things are going to get a little bit more interesting is when we talk about humidification and dehumidification. And so we'll get into the details and we'll work through some of the mathematics of this, but I first wanted to introduce kind of what we're going to expect in terms of movement on the psychrometric chart. So in terms of the humidification process, what we're going to be doing is we're going to take some flow in, and for simplicity, let's just call this state 1 and we'll call this state 2. So this would be 2, this would be 1. And so we're going to have the moist air come in. So we'll have a temperature 1, we'll have a humidity ratio 1, we'll have relative humidity 1. And then it's going to leave at some temperature, some different humidity ratio, and some relative humidity at state 2. And so what we're doing for the humidification case is we're going to add some water. So we're going to have some mass weight of water. It's coming in, and the addition of the water into the system, that's going to cause the mass of the water vapor to increase. And so we expect in this case the humidity ratio at state 2 to be greater than the humidity ratio at state 1. And so we could get to this because we could do, okay, for air, mass flow of air is going to remain constant through the system because it's a one inlet, one outlet for air. And so if we said we know that the humidity ratio is the mass of the water vapor divided by the mass of the dry air. Mass of the dry air is constant through this. We've increased the mass of the vapor in the system, so we expect the humidity ratio at state 2 to increase. So this value will increase, therefore we expect W2 to also increase. And so we expect our process to do something different on the psychometric chart at this point. And so to demonstrate this, let's go ahead and first choose a state point, and we'll call this state point 1. So state point 1, T1, this is going to equal 30 degrees Celsius. We had a relative humidity of 30% in this case. And so if we want to now add water vapor, we know that we have to move up because on the y-axis over here, this was the humidity ratio. So if we drew a line over here, this would be essentially W1, and we know that W2 has to be greater than W1. So we have to move vertically in this psychometric chart. Now the question becomes, is it vertically straight upwards? Is it vertical with some right component? Is it vertical to some left component? Is it is it case dependent? And so that's the question that we really have to ask ourselves. And so we'll get into the mathematics behind this in a few minutes. But what we're going to see is it's actually a case dependent process. And so it's going to depend on how we add the water into the system. If we add water as a liquid, the water that's sprayed into the air has to start as a liquid, change phase from a liquid to a vapor, and then basically get to the same temperature as the air. And so if we do liquid water into the system, well, it's going to take energy from the air to cause the phase change of the water. So the air is going to cool down, the water is going to go through the phase change, and then they have to kind of come into an equilibrium. And we said, well, if we think about that for a minute, we kind of talked about a case that sounded kind of similar to that. And that was actually last Thursday when we talked about the adiabatic saturation temperature. We said we took water that was about the temperature of the air. We put that water into the air until we reached a saturation condition, but we had no outside heat transfer. And so we note here we have no heat transfer. So it's going to basically be that adiabatic saturation case, but we're not going to necessarily end up at the saturation condition. And so what we'll do is we'll move up and to the left because we want to move like it's going to be one of the adiabatic saturation conditions. And what we'll note is that adding liquid water, so we'll note that this is a liquid water, we will be able to approximate this as a wet bulb temperature equaling a constant. That's going to be the base assumption that we have for this system. And so remember, the wet bulb temperature was the temperature that we'd read if we drew our diagonal line up to this point. And so this would be T wet bulb. And so state 2 is going to be on the same wet bulb temperature line as state 1, which again is going to be this diagonal line that roughly follows these solid black lines, which were the lines of constant enthalpy. And so in this case, we are going to be taking energy from the air. It's going to cool the air down. And so what this process is this is evaporative humidification. or we could call this evaporative cooling. And so we're basically cooling the air temperature down by causing the water that is entering the air to go through a phase change. And so again, if we have liquid water, it's going to go diagonal up and to the left along the line of constant wet bulb temperature, because we'll assume that the water is pretty close to the air temperature in that regard. Now let's think back to the other case that we wanted to talk about. And so we said, well, that was only if we put liquid water into the air. What happens if we put vapor water into the air? And so vapor water means that we just boiled the water before we sprayed it into the air. So basically we have steam addition. And so steam is going to be much warmer, and it's going to generally also not have to go through that phase change because we've already put the energy in for that phase change. And what we'll see is that for steam addition, we will move up and to the left, or to the right, sorry. So this is going to be state 2. And this is going to be for steam addition. And we'll talk about why this is, and we'll show the mathematics of this in the next few slides. But again, it's going to always move up. So we see for both of these cases, we see that the humidity ratio for 2 is going to be greater than 1. And if we did it over here, we'd see the same thing for this first point. We'll also see that we also would expect, but it's not always going to be the case, but we generally expect that the relative humidity is also going to increase. So in this case where we did the evaporative cooling, it increased from our about 20% up to about 60%. And in this case where we did the steam addition, we increased it up to about 40%, where we had the temperature now increase. So steam addition, T2 will generally be greater than T1. For the evaporative cooling, we would expect T2 to be less than T1. So again, cooling the temperature down. And so again, we'll get through the mathematics on this in the coming slides. Okay, so we will talk about the special case of cooling and dehumidification in a little bit later slide. But while we were talking about kind of the constant wet bulb temperature process, I wanted to introduce a separate type of dehumidification that we don't necessarily always talk about, but I think it's worth at least mentioning it. So if you ever hear about this in terms of kind of like a specialized kind of a requirement, it is going to be called the desiccant dehumidification. Now, desiccant dehumidification, I'm going to have to erase a little bit of this region down here, is a kind of specialized version for kind of low temperature, I would say low relative humidity processes. And so this would be most common if you're working in a very specialized design environment, so manufacturing, where you need a very low relative humidity, possibly a hospital environment. You'll use a desiccant dehumidification process. And so what the desiccant dehumidification process is it's the exact same thing as the evaporative cooling, except it's going to be in reverse. And so what we do is we have a desiccant wheel. Desiccant wheel is basically a substance that when the water vapor passes over it, it pulls the water out of the air and it traps it in the solid substance. And so what it will do is it will take state 1, it will take state 2. We will decrease the amount of water that's in the air, and we will do it along a constant wet bulb temperature. So this is kind of the specialized case. And so this is, again, we refer to this as desiccant dehumidification. And again, this is only done when we're really far over here on the left-hand side. So the process when it adds, so when we add steam addition to it, basically, again, it's going to be like, I call it some heat addition. So basically you're going to be doing, I guess there's really no special term for that that I can think of off the top of my head, but basically it's going to be steam humidification versus kind of the liquid water, which we usually say is more like an evaporative cooling process. So you just have to look at the state of the water generally when you refer to that process. Okay. Yeah, so I just wanted to note, again, desiccant dehumidification would be the same as the evaporative cooling, just in the opposite case, because we're using a chemical to pull the water vapor out of the air. And again, it's done very far to the left-hand side of the psychometric chart for purposes of like electronics manufacture. So if you're ever dealing with an electronics manufacturer, you need really low relative humidity. You can get it very low. And so this would be the process. Now it's going to be different from how we will generally talk about dehumidification, which will be done in the cooling and dehumidification case. But I just wanted to introduce it to you. If you ever run into that in industry, you'll at least kind of have an understanding of what's going on. One other thing to note on desiccant dehumidification is basically if you ever think of what is a desiccant, kind of the most common application is if you have like a substance that needs to stay dry. So if you ever open a pack of like beef jerky that needed to stay dry, sometimes you'll see a little container inside of that. Basically, a desiccant is to keep some sort of substance that helps keep the water vapor, bring it out, and prevent that from getting in the food. So that would be like an example. Other times, sometimes if you buy like a new pair of shoes or something like that, you'll find little packages of like a kind of a small little container inside of it. Air can get through it. Those would also contain small little pieces of desiccant to keep the moisture from essentially being inside of a shoe. So you do see desiccant in kind of some applications, generally products that you don't want water vapor to form in. So that's another reason why I wanted to point that out. Okay. So moving on, let's go ahead and put some concepts together. So generally, when we talk about HVAC applications, we're going to be doing multiple steps together. And so the most common way to think about HVAC systems is if it's cold, it's January in Milwaukee, we need to change the outside temperature to make it essentially when we bring air into our building, we need to get it up to kind of human comfort standards. And so in terms of Milwaukee, let's say the temperature we'll use 5 degrees Celsius and we'll say that it's maybe 50% relative humidity. So somewhere like right here, we'll say is the outdoor temperature. So maybe 5 degrees Celsius, that's late fall, early springtime. So this is our outside temperature. And we want to bring this air in and we want to heat it up. We want to make it comfortable for our living conditions. And so what we're going to do is we're going to do a combined heating and humidification process. And so the reason we want to do both heating and humidification is the first thing that we want to do is we want to get it up to somewhere around the temperature we want to be. So let's say we want things to be maybe about 25 degrees Celsius. So we're going to do our base just simple heating process. And we'll now have the temperature right about where we say it might be comfortable in terms of, about room temperature. So that might be a little bit on the warmer side. And so again, this is just our simple heating process. Now we note that for the simple heating process, we know the humidity ratio at 1 has to equal the humidity ratio of 2. But we said the relative humidity at 1 is going to be greater than the relative humidity at 2. And so we are going to be decreasing the humidity, relative humidity, as we've increased this temperature. Now, why this is important is human comfort considerations come in. If we have a very, very low relative humidity, we aren't very comfortable. Our skin starts to get dry. It's not always the best thing for us. And so we generally find that for most kind of buildings, if you want to be on the low end, 30% relative humidity is probably a target range. On the upper end, maybe 60% relative humidity is kind of the upper end of that comfort. You also have to consider something like mold growth and things like that. So generally you want to keep it a little bit on the lower side, but we'll say 30 to 60% relative humidity is something that we're going to target. And so what we've seen is by adding just heat in, we've now decreased the relative humidity. This isn't going to be comfortable for us in an environment. And so we need to use the humidifier to make this process be very comfortable. And so if we used a steam humidifier, we would again move up and to the right. And so we could increase this up to maybe, we'll just do up to 40% here. So this is going to be state 3. We'll note that the humidity at state 3 is going to be greater than the humidity ratio at state 2. And so now it's a little bit warmer than we probably intended. It's going to be about 27 degrees Celsius, but for human comfort, we said, okay, that seems reasonable. And so that will be the process that we would do for or basically just doing heating and humidification. Now, if we wanted to do the same thing except with now evaporative cooling, well, we'd probably take a hit here. So let's say we ended up right about here. Well, we have that line of constant wet bulb temperature. This would be state 3 if we did that. And so we're back down to about 20 degrees. So we'd probably have to heat it up a little bit more if we were to do evaporative cooling in this process, because now this is going to be a little bit cold for human comfort. But we'd have to adjust our settings based on what type of process we do. So this is just an example of how we could target different conditions for human comfort. And so we're going to have to work through the mathematics on this. So that's going to be what we do on the next slide. Is we're going to go ahead and work the math and set up all of the equations necessary to do a heating and humidification calculation. And so again, basically this is what we're going to be talking about. And we're going to talk about why these lines have different slopes to them at the end of this analysis. And so in terms of heating and humidification, I just remember there's one other thing I wanted to point out. The other reason that we do heating before the humidification is we decrease the relative humidity at the exit point, which makes it easier for the water to evaporate into the air. So technically, if we wanted to, we could have added steam here, and then we could have gone over to this point. But we would have been at a very high relative humidity at this point, and it'd be harder for us to add water vapor into the air because there's less potential for the air to take on that water. And so what we do is we heat it up first to increase the amount of water that the air could potentially take on, and then we do that humidification process. So that was the other thing I wanted to note is lower relative humidities will make it easier to put the air into the system. Okay, now let's go ahead and get into some of the mathematics. So the first thing that we're going to focus on is how do we first model the heating, and then we're going to do the humidification. So what we're going to do is we're going to block this into separate parts. And so you'll do this for your analysis. You're going to see that we have one region where we have from 1 to 2. This is just going to be our simple heat addition. So we have Q in, or Q dot in this case, open system. So we'll have heat addition in. We'll note that we'll have the states 1 and 2, there was no mass transfer. So we'll eventually be able to show that the humidity ratio at 2 is equal to the humidity ratio at 1. And then from state 2 to state 3, we're going to be putting some mass of liquid water into the system, and we'll note that it's a flow rate. So we'll do an m dot water in. And so we're going to be increasing the amount of water vapor flowing through the system, but it's going to have no heat transfer. And so when we break this system down now into 2 parts, we have a process 1 to 2, and this is just going to be simple heating. Now in terms of process 1 to 2, we're going to have 3 main equations that we want to work through. And those 3 main equations are going to be conservation of mass and conservation of energy. And so in terms of conservation of mass, we have first the air that needs to be considered. And so we can say that we have the change in the mass of the air with respect to time inside the system. We're going to apply our steady state assumption to get that to go away. And we'll have the mass flow rate of the dry air coming in minus the mass flow rate of the dry air leaving. And so we'll note that the mass flow rate of the dry air at 1 has to equal the mass flow rate of the dry air at 2. And we'll just be able to notate that mass flow rate of the dry air because that's just a single inlet, single outlet. Mass flow makes our life easy. Now, in terms of the second equation, we'll repeat this for conservation of mass. We'll do this for the water and the water vapor. So we'll note that the change in the mass of the water with respect to time inside of our system, this is going to go to 0, and this is going to give us the balance. Now, in terms of the system, we have the mass flow rate of the water vapor coming in and the mass flow rate of the water vapor leaving. So m dot vapor 1 minus m dot vapor 2. And we end up with the mass flow rate of the vapor at 1 has to equal the mass flow rate of the vapor at state 2. Noting that the mass flow rate of the vapor, this would equal the humidity ratio times the mass flow rate of the dry air. When we now substitute in this equation into this, what we'll find is the humidity ratio of 1 has to equal the humidity ratio of 2. And so that is the first thing that we can get out of this. We already kind of discussed that. We said that was the kind of reasonable outcome we expected, but now we can show that mathematically. Okay, so moving on to the next set of equations that we want, and this is going to be conservation of energy. We can say the change in energy inside of our system with respect to time. This is going to go to 0, applying the steady state assumption. This is equal to the heat transfer rate in minus the rate of works out, plus then we have the sum of the mass flow rates in times the enthalpy in plus the kinetic energy in plus the potential energy in, and there'll be parenthesis, minus the sum of the mass flow rates out times the enthalpy out plus the kinetic energy plus the potential energy. We said, well, thermo, we generally assumed that we could get rid of kinetic and potential. That was like 1,000 times smaller than our thermal energy, our enthalpy. And so what we're left with, assuming, again, we don't have any work interactions, we just had the heat transfer into the system, we end up with 0. This is equal to the heat transfer into the system. And now we have to break apart our mass flow rates. And so in terms of our first mass flow rate, we had air. So we had the mass flow rate of the dry air coming in, and that was the same as the mass flow rate leaving, so we can combine those together. We have the enthalpy of air at state 1 minus the enthalpy of the dry air at state 2. And then we have to account for the water vapor. So we have the mass flow rate of the vapor. Noting the mass flow rate of the vapor at 1 and vapor of 2 are the same. I'm just going to go ahead and use the nomenclature 1. We now have the humidity ratio of the, so we can say now we have the mass flow rates here. We can now relate it to the enthalpy of the vapors. So this will be H sub G1 minus now the enthalpy of the vapor leaving H sub G2. Now what we generally want to do is we want to get the analysis done on a dry air basis. And so what we're going to do is we're going to make this substitution right here. We're going to relate that to our humidity ratios. And so what we end up with is we have 0. This is going to equal the heat transfer rate in. Then we have plus, we have the mass flow rate of the dry air. We then have the enthalpy of the dry air at state 1. Plus, then we're going to have the mass flow rate of the vapor divided by the mass flow of dry air. That gave us the humidity ratio at 1 times H sub G1. Put a parenthesis in a parenthesis. Then we have minus, this would be parenthesis H sub air 2, plus the humidity ratio at state 2, H sub G2, parenthesis. And then that was the last part, so we can do another parenthesis there. Now what we're going to do is we said, well, we can go ahead and do a little bit of a substitution here. We can say this value would be the enthalpy of the dry air, or basically the enthalpy on a dry air analysis. And so we can say that this is kind of like an H1, and this value over here, this is our enthalpy at 2. So again, this is the enthalpy per unit mass of dry air, because it's on the dry air analysis. And so if we go ahead and come over here and we solve for this setup, well, we can now get the heat transfer rate in. Well, this is just the mass flow rate of the dry air times now the enthalpy of the combined water air on the per unit mass of dry air set up at state 2 minus the enthalpy of that set up at state 1. And we'll note that in this case, the enthalpy, this would be enthalpy of the dry air plus the humidity ratio times H sub G, which we can now relate to C sub P times the temperature at state 1 or state 2 plus the humidity ratio times H sub G. And we'll note that this temperature for our purposes will be in degrees Celsius, not Kelvin. So that is the one note. And so doing this lookup, this H that we can get here, if we wanted to look that up on the psychometric chart, that is right along the top here. This is that combined H per unit mass of dry air. And so that's what we've done for this process is we can now use the psychometric chart. We just have to figure out what the enthalpies are, and we can figure out our heat transfer rate just by knowing the mass flow rates. And so that's really nice and that's useful. And that is for our simple heat addition. We said that worked out great. We can now just know the mass flow rates. This is just like what we saw for heat transfer in Thermo 1, Thermo 2. So that is a pretty good result. Now where things get a little bit more interesting is when we deal with process 2 to 3. So this is going to be our second process, and this was the humidification. Now for humidification, we want to add the mass of the water coming in, right? So we're doing a mass change in the water vapor. And so that's the big thing that we have to take into account for process 2 to 3. We're adding water and we're trying to get that to evaporate, or if we added steam into the system, we want that to essentially stay in the air. We want it to increase the amount of water vapor that we have. And so what we're going to do is we're going to go ahead and do a conservation of mass. We'll do this for the air first. And what we'll note is the mass flow rate of air at state 3 has to equal the mass flow rate of air at state 2, which we can say is just the same mass flow rate of dry air. So basically, dry air came in at state 1 and just went straight through. There was no change in that mass. And so that makes our life easier. We can just say everything relates to that same flow rate of dry air. Now, where things get a little bit more intricate is where we have to deal with the conservation of mass for the water and the water vapor. And so writing this out, the conservation of mass, dm water dt, goes to 0 because it's steady state. But we now have the mass flow rate of the vapor at state 2. We have the mass flow rate of the vapor at state 3. And we now have this mass flow rate of liquid water coming in. And so we have the inflows, mass flow of vapor 2, plus the mass flow rate of the water coming in, minus now the mass flow rate of the vapor at state 3. Resolving this, we can go ahead and find the mass flow rate of the liquid water. So we go the mass flow rate of the vapor at state 3, minus the mass flow rate of the vapor at state 2. Now, what we're going to do is we'll again apply the assumption that m dot vapor, this can be the humidity ratio times the mass flow rate of dry air. Noting that the dry air for state 3 and state 2 is of course the same. What we'll get is the mass flow rate of the water that we use to add the water into the system. This is going to equal the mass flow rate of the dry air times the humidity ratio at state 3 minus the humidity ratio at state 2. And so this is going to be one of the key equations that we're going to need moving forward. Okay, so now that we have that equation, we said 2 conservations of mass, 1 conservation of energy. So let's go ahead and deal with our third equation, conservation of energy. And here we have dE dt, so change in energy inside the system. We're going to assume that it's at steady state, so we'll go ahead and let that go to 0. We then have the heat transfer rate in. We said there's no heat transfers, there's only mass transfer, so no heat transfer rate in. We'll do minus the rate of work out. We have no turbines or compressors, so work out is 0. So then we have plus the summation of the mass flow rates in, enthalpy in, plus the kinetic energy, plus the potential energy. We're going to neglect those, and then we can do the same thing for the outflows. So minus the mass flow rate out, enthalpy of the flow out, plus the kinetic energy, plus the potential energy. And we'll get rid of the kinetic and the potential energies. And so what we see here is this just becomes a energy balance between the different mass flows. And so accounting for our different mass flows, we had the mass flow rate of the dry air. We have the enthalpy of the air at state 2 minus the enthalpy of the dry air at state 3. Then we have plus the mass flow rate of the vapor coming in at state 2. Multiply that by the enthalpy of the water vapor at state 2. We then have plus the mass flow rate of the liquid water. We'll use H sub W for our liquid water, and we don't know it's liquid at this point. Actually, we'll just use that for whatever water that we're going to add. We can change that if we need to. And so if we've done that, then we have the last part, which is the mass flow rates leaving. So we have the mass flow rate of the vapor at state 3 times H sub G3. Now, what we can do is we can go ahead and rearrange this. We can do this on the dry air basis, and what we'll end up with is 0, so equal the mass flow rate of the dry air. We'll have H of the air at state 2, so dry air plus the humidity ratio at state 2, H sub G2. And we'll go ahead and put a parenthesis in a parenthesis there. We have minus the H of the dry air at state 3, plus the humidity ratio at state 3, H sub G3, put a parenthesis there. And then we have plus, and we have to deal with this mass flow rate of the water. Now what we're going to do for this mass flow rate of the water is we're going to use the boxed equation up here. We're going to make this substitution in. We see we can pull the mass flow rate of dry air out, and we'll end up with the humidity ratio at state 3 minus the humidity ratio now at state 2 times the enthalpy of the water, and we can go ahead and put a box around that, or end the parenthesis. Okay, so that is really going to be helpful because we see we've bracketed in here. This is what we referred to as the enthalpy at state 2. This is essentially the combined dry air enthalpy here at state 3. So it's on the per unit mass flow of dry air. So we could get those from the psych chart. And so if we go ahead and just rearrange this one more time, we get 0. This is equal to H2 minus H3. Plus now we have W3 minus W2 times H sub W. Okay, now what this is going to let us do, and we're going to do this quick trick, that is going to give us the enthalpy of the water. This would equal, and if we rearrange this, it would be H3 minus H2 divided by W3 minus W2. And so what we could say is this is basically a change in enthalpy over a change in the humidity ratio. Now, why is this result special? Well, short answer is there's something on the psychometric chart that we didn't show you before. That is, if we go back to this chart, there is this protractor up here in the top left corner. And in this protractor, there is a value right here that is the enthalpy per humidity ratio. And so this value is a delta H over a delta W. And so if we know a delta H over delta W, this is equal to the enthalpy of the water that we're bringing in. And so if we know the enthalpy of the water coming in, we can now use that enthalpy and we can look it up on this protractor. Now the key thing about this is the enthalpy on the protractor here, this is going to be in a megajoule per kilogram. So we have to take whatever value we look up and basically divide by 1,000. Now what we can do is if we go ahead and look at our appendix, we can say, well, about room temperature water, that's about 83 kilojoules per kilogram. And so 83 divided by 1,000, 0.08. So if we go ahead and take 0.08 on this protractor, here's 0.08, that's going to be somewhere over here. And I'm going to try and draw this somewhat right. And if we look, we said that line that we just drew, it's not perfect, but that looks an awfully lot like the T wet bulb is equal to a constant. And so anytime we add liquid water into the system, we basically can approximate that by a wet bulb temperature equaling a constant. And again, we can see that it's going to move along this line because that's the line that we had on the protractor. Now, if we wanted to repeat this one more time and do this instead for steam, so room temperature, we've heated steam up to get water to go through the phase change. That's about 100 degrees Celsius. So the enthalpy of water vapor will be about 20. So getting into megajoules, 2.67. And so if we go look at the protractor, 2.5, 2.6, 2.67, we'll see that it ends up being an almost vertical line. So when we do add steam into the system, it's almost going to be straight vertical because the energy is basically going to be, energy addition is going to be minimal because it's only a small amount of vapor. So slight increase in temperature, but we're going to really just get the humidity ratio up. But again, if we do it in a liquid form, it's going to cool the air down because we have to put all of that energy in to first go through the phase change, then get the water vapor to the same temperature as the air. And so that's why we have the cooling. And so again, the direction that it moves during the evaporation or the humidification process is going to be related to the enthalpy of the water that's added. So if we add water, so liquid water, this value will be H sub F. If it's steam, we will use H sub G. And so those two values are very different at a given temperature. And that is, again, why we have the difference in the angles and why we have this protractor on the psychrometric chart. Okay, so that is going to be the end of today's lecture. We'll pick up tomorrow with the next portion, which is going to be the cooling and dehumidification. And then we'll work into adiabatic mixing. And then we'll talk about, I think we should be able to start an example problem as well. So again, that is the plan for tomorrow. It looks like I have a question.
Oh, yeah, I had two questions. One, could you go back to the heating and humidification phase? Thank you. And then two, did you say that we have all the info for the psychrometric chart quiz?
I was going to say you might, maybe at this point, since I was hoping to get through this slide as well, you might want to hold off until tomorrow's lecture to do that. At that point, you will have everything, just to make sure you can answer all of the questions. But
okay, cool.
Hopefully you should be able to have most of it at this point. It's just about getting through this last part.
Got it. Thank you.